Hello, we are still with the Ising model, and we'll be with the Ising model probably till the end of the semester. I will just remind you what the Ising model is. So we try to describe a behavior of a magnetic system, okay, where quite interesting phenomena occurs, specifically a phase transition, hysteresis loops, and etc. We assume that on each point on our lattice there is a particle. The particle can have a spin which is either +1 or -1. This lattice can be one-dimensional, two-dimensional, three-dimensional, n-dimensional lattice in general. Okay, so at each lattice there is plus or minus. This is I, this is particle J, okay, and the energy is minus a sum over I mu 0 H. H is the external magnetic field, SI, minus 1/2 sum over J, sum over I, coupling constant J, which depends on the distance between the particle. This is particle I. The position of the particle I is Ri. The position of particle J is Rj, vector, vector. So the coupling depends on the Ri minus Rj. And here we have a multiplication of Si Sj. Okay. So why we need this term? As we explained already, we try to follow the following rule. We want eventually different particles to point somehow in the same direction, and if they are pointing exactly in the same direction, the energy or this state becomes preferable, meaning the energy becomes smaller. Okay, so this is why we have Si multiplied by Sj. When they are exactly in the same direction, Si multiplies, so this is +1 and +1, this is positive, J is always positive. Just write it down. So J Ri minus Rj is a positive coupling constant. So in total, this term is positive, and because of the minus sum sign over here, it's negative. Okay, what have we seen so far? We've solved for the non-interaction case. Basically, when J equals exactly 0, so we completely don't care about all the one spin behaves on its own, it doesn't really care about everybody else. Okay, we managed to solve and obtain that the partition function equals exactly to 2 hyperbolic cosine of beta mu 0 h to the power n. Okay, and the average magnetization was equals to mu 0 n hyperbolic tangents of beta mu 0 h. Okay. Now when we look on this guy, this is our average magnetization. Okay. So if we plot the average magnetization as a function of the temperature, okay, we notice that for the H equals 0, okay, for the case when there is no external field, hyperbolic tangents of 0 is what? It's always 0. So the average magnetization is independent of the temperature, independent of beta, and it's always 0. Okay? And it's always 0. So it is definitely not the behavior that was observed in experiment when we expect an existence of a critical temperature or Curie temperature below which the system goes from the paramagnetic behavior, and this is a paramagnetic behavior. We'll write it down. This is for H equals 0. Okay, to ferromagnetic behavior. There is no transition, right? We would observe a non-zero magnetization, all right, when the external field is non-zero. Okay, and there should be some sort of a behavior for in the non-zero case. So this is H equals 0. We will have something that looks like this for H greater than 0. We will see something that looks absolutely negative. If we look on this guy, okay, this is H smaller than 0. But this is to be expected. You apply an external field, you get a net magnetization. You apply a negative magnetic field, you get the opposite net magnetization. You do not apply an external field, the net magnetization is 0. And this is why? Because we assume that the system is disordered enough, so there is a symmetry. Okay. So the only chance in order that we can maybe observe something that will remind us of the experimental results is actually to include this interaction part. Now, and if you think about it, it's absolutely clear that without any interactions, all the particles shouldn't produce any ferromagnetic behavior. Why? Because if this particle is pointing up and it's not affecting any other particles, the other particle can point down. They will just kill each other. This positive inner magnetization will kill the negative one, and total net magnetization will always be 0. So this is the symmetric case. Without any interactions, there is no preferential direction. Okay. Let's see if we can actually get some sort of magnetization when we include this magnetization or this coupling over there. Now, what is the problem of actually dealing with the coupling? It's, so we have this term. This is a simple sum. This is a double sum. What's the big deal about this coupling? So let's look again on the total energy. So we have this first term, minus I, mu 0 h Si, minus 1/2, sum over j, sum over I, this j, Ri minus Rj, okay, Si Sj. What is the big deal about this? Now, what exactly have we done, okay, when we solve the non-interacting case? This was not present. We looked on e to the power beta over a sum over I mu 0 h Si, and we simply said that this guy is what? It is e to the power beta s mu 0 h S1 multiplied by e to the power beta mu 0 h S2 multiplied by e to the power beta mu 0 h S3, etc., etc., etc. So it is extremely simple to obtain when you have only from the non-interacting case, from this part, the factorization. Okay? How we solve problems in statistical mechanics. Eventually, we somehow look on the system, we can say we can separate it into a group of non-interacting particles. So here it's extremely simple to perform this, right? Because exponent of a sum is a product of many exponentials. Okay? So one can say, well, maybe I can do the same trick when I have this double summation, right? The problem is, if I write down the first exponent, so it will have e to the power beta mu 0 h S1, okay? But S1, this is not the only term where S1 appears. There is also all these others S1s. So we'll say, well, yeah, let's take this out, and we'll just write down plus beta divided by 2, a sum S1, okay, a sum over J, okay, J of Rj minus R1, okay, and here I will have Sj. Right? Let's multiply it by the next term. The next term will be e to the power of beta mu 0 hs2 plus beta divided by 2 s2, a sum over what? Over j of rj minus r2 s2 or sj. Okay? And we'll continue this multiplication on and on and on. Now, you notice that while here in the first exponent only S1 was present, over there all the other Sj's are present. For S2, it's not only the presence of S2, there is also the other terms S1, S3, S4, S5, everybody else are present as well, right? And the difficulty is to somehow separate those other Sj's and kick them out of my simple exponential, okay? Now, what have to be done? We need to find some sort of representation of the original spins, use some other variables, right? Such that eventually we'll obtain a multiplication of independent terms, of independent exponentials. We know how to do it only for two cases, the simple one-dimensional case and a very specific case in 2 dimensions. That's it. Most of the time, and for a very specific form of this coupling constant, most of this time we cannot simply separate, because you see we'll always have some correlations or dependence of this term and the next term, okay? Because S1 and S2 are present over here, and in S1 and S2 they are present over there. So this and this are not independent, and when we sum up over different realizations, okay, we cannot simply sum only on the realization of S1 and independently on the realization of S2. They are penetrating to both expressions. So what one can do? Well, I'm not going to show you how exactly to solve this in the one-dimensional case or two-dimensional case, because it's actually extremely lengthy calculation, especially in the 2D case. It will take us at least 3 or 4 lectures, very, very, very long. The one-dimensional case, it's not so long, but it won't teach us something. But people invented a technique, okay, that can actually get us a little bit forward. Okay, so we can think about it mathematically, and the mathematical problem here, they are correlated, and we need to find a transformation to different variables that we don't know how to think about it. Or we can say, what actually is the physics of this problem? Okay, let's try and present the method of solution of this problem. When I have interaction, I'm not capable of doing everything mathematically. Okay, so mathematically is a very hard problem, and I'm stuck. Okay, so I'm trying to look on the physics of the problem and use the physics of the problem in order to solve the my mathematical problem. Okay, so what's the physics? Okay. Let's look on our particle over there. This is our Ri. The spin is Si. It can be either +1 or -1. What is the problem? So there is a mathematical difficulty. The problem is that the energy depends not only on this guy, but it actually depends on what are the different values of its neighbors, right? Or all the other different particles. The other particles affect this guy. Why? Because we have a coupling term, okay? And in the similar fashion, this guy also affects the other guys or its neighbors, right? And this is the trick part, because there is a mutual interaction between those two. The value of Si affects Sj, and the value of Sj affects Si, and and then this is our mathematical problem. Now we can look on the situation and we can say the following thing. Well, there is only one single spin, Si. We're concentrating on this guy, okay? And there is huge number of different other spins, right? So this is the purple guy, and we have many, many, many other spins that are, bad marker, sorry. Many other spins that are sitting all around it, okay? And somehow they affect our single spin, okay? There are a lot of them, huge number of them. We can say, look, so what's actually happening? What's actually happening that all of them affect our one single guy, and somehow this guy is also affecting them backwards. Okay, there's a lot of them, and he is only one. So let's assume that somehow effectively the total magnetization of all of its neighbors create an effective magnetic field, we can call it M, that affects this guy. Okay? So what I'm saying is there is an interaction between Si and all the other spins. We can assume that this interaction occurs through an effective field. So instead of using this representation, we somehow need to model this or approximate this by what? By saying there is an effective interaction, okay, we call it mean field, okay, that all the other spins are implying on our single spin, right? And if we will know what is this effective mean field, okay, we can solve the problem. Right? So the question is, what is this effective mean field? We don't really know, but we will say if there is an effective field, we might solve the problem, right? Because maybe we can neglect the problematic interaction over there and use some effective approximation. This idea is called the mean field approximation. Mean field approximation. Okay. It's a standard technique in physics when you have a huge number of interaction terms and you just say, well, instead of using this all different terms of interaction, I assume that they all affect somehow effectively as an external field. I don't really know what the field is, but let's assume that there is a field and let's find out what's actually happens inside. Okay, so how exactly one go on beyond just saying, well, there is an effective field? You do the following approximation, right? The problem is that we have Si and Sj's. Okay, this is the problematic multiplication that we have in our energy over there. Okay, so instead of saying Si and Sj, we can say the following, and this is exact. There is still no approximation over here. So let's assume that our external field that is applied on our system, we call it M. Okay. So Si, we can use this M by saying that Si is just simply M plus Si minus M. And Sj is again simply this M plus Sj minus M. So we haven't done anything yet. Okay? This is exact. Let's open this parenthesis, and what we will get the following. We will get M squared, okay? We'll get this guy multiplied by M, okay? M Si minus M, okay? We will get an additional term, that this term multiplied by M plus M multiplied by Sj minus M. And then we have the small term, which is Si minus M Sj minus M. Now what usually physicists do? Physicists say the following: there is an external field. This field is M. it is strong and it affects strongly the single spin. There are some fluctuations of my spin around this effective external field. Why there are fluctuations? Because, you know, I can flip. It's this, there is temperature, non-zero temperature. So everybody else are affecting on me, on my condition over there. I prefer to point exactly the same direction as they all pointing, but I can actually sometimes change my direction, okay, because there are temperature. And it's possible. Okay. I'm not going to change my direction too much. I'm going to change it a little bit. Okay. So if I'm looking on this term, I can say the main contribution comes from this guy, this m squared. There are corrections because I'm changing my directions. Where are the corrections? This term and this term are the first order corrections. Okay. Now I have also additional corrections, right? Let's neglect them, right? We have to neglect something because otherwise it will be an exact solution, but we have to neglect something, so we are neglecting the second order fluctuations. Okay? Makes sense so far, right? Yep. No, because I'm saying that Si minus m is small.
I understand.
Yes.
Still there's the
Because I'm keeping m squared. You see, m is big, Si minus m is small. So Si minus m to the second power is smaller. All right? So I'm not neglecting m, I'm neglecting Si minus m. This is why I had to write this down in this fashion over here. You're right, I cannot neglect m, okay? But I can neglect the small term multiplied by the small term. Okay, so we are now going backwards to our interaction term. Okay, so what is the interaction term? The interaction term, let's write it down as sum over j, sum over I, j of Ri minus Rj, something something, Si is j. Okay. All right, so instead of Si as j, we are using our mean field approximation. Okay, there is an external field. We have small fluctuations around this field. Okay? So we're getting that there is a sum over j, sum over I, j of Ri minus Rj, okay, multiplied by what? So what we have inside? We have m squared plus m Si minus m plus m Sj minus m. Okay? So you can already see that this is somehow solvable. Why it's solvable? This is approximately. Why it's solvable? Because we do not really have a double sum anymore. Okay? There is no Si as j. And if there is no double sum, maybe, not maybe, but definitely, we can get backwards to the solution of a non-interacting system that we have done previously. Okay? So this is the idea. The problem is, we don't know what this m is. Okay? So we will need some additional information or some additional physical intuition in order to get the grip or the handle over what m is. Right? But for now, there is m. Let's assume that it's not zero and that it's big. Right? And let's solve everything when this m is present over here. Okay, so let's see what happens. So our first guy is simply a sum over j, a sum over I, okay, j, okay, this is the first term, j Ri minus Rj, okay, m squared. Okay. Now, what we are assuming, we can get m squared out of this. Okay. We will have a sum over I, And here we have a sum over J, coupling constant, Ri minus Rj. Okay. Now, this is a deterministic coupling constant. It's not a stochastic random variable. It does not change its sign. It does not change its value. So we can sum up over all the different coupling constants. We will see an example. Okay? We're just performing the summation. We can sum over it. So let's call all of this sum J tilde. Why I don't have in this J tilde J dependence or I dependence? I'm summing up over all the different I's and all the different J's. Why I'm not basically saying, well, there is J tilde and it will depend on I. Okay? I'm simply not saying that. I'm saying all of this, the sum is simply J tilde. Why? Because I'm assuming that my system is extremely large. And it really doesn't matter what is the center of my system, because it's macroscopically large. Right? So if I will start from here and I sum over everybody, it doesn't matter. It won't change if I will start my summation from this direction. Okay? Or I can assume that my system has a periodic boundary conditions, so it doesn't matter where I pin my center. Okay? So this summation is independent of Ri. So what are we getting here? That this equals to m squared J tilde sum over I, okay, which is 1. This is simply n m squared J tilde. This is the first part, this guy. Okay, so this is 1, this is 2, and this is 3. Okay. What happens for the second term in the summation? We have a sum over J, a sum over I, okay, J, Ri minus Rj. Here what we have, M, Si minus M. Okay, so we are simply saying this is what? This is a sum over J, a sum over I, J, Ri minus Rj multiplied by M and Si, right? Minus M squared J tilde multiplied by N. You agree with me? So the minus term came from this guy multiplied by that guy. Okay. Now I'm looking on this term. Here I have a summation over J, summation over I, J, Ri minus Rj, Si. Okay? The order of the summation is not important. So I can say that it equals to M, a sum over I, Si, okay? And here I have the summation over J, J, Ri minus Rj, and that's it. Now this guy is again J tilde, okay? So overall I have M, J tilde, a sum over I, Si, minus, we have this term over here, it's minus M squared J tilde N minus M squared J tilde N. Okay. Now, what is the difference between the second part and the third part? So the only difference is that instead of Si, I have Sj. What it will cause? It caused that when I here at first summed over J and then afterwards I summed over I, okay? But if I will have here Sj, I will first sum over I and afterwards over J. Okay, so the third part is easy. A sum over J, a sum over I, J of Ri minus Rj S, what do we had over here? M Sj minus M equals to M J tilde as sum over J Sj minus M squared J tilde N. Now, I and J over here are simply dummy variables. Okay? It doesn't matter if I'm summing over I or I'm summing over J. I'm just summing over all the spins. Now, at this point we are done. Why we are done? Because this is a constant. Okay, we don't know what M is, but it's a constant. Okay? This also a constant. The same goes for this term. And this summation over here, it resembles the summation of the non-interacting case. Okay? Let us write down this mean field approximation. So E, again, was equals to minus a sum over I, mu 0 H Si, minus 1/2 sum over I, sum over J, J Ri minus Rj, Si, Sj, okay? And what we have shown that all of this equals to, so the first term is exactly the same, minus I mu 0 H Si. Now, what we have minus 1/2, and what we put inside. So we have N M squared J tilde. We have from this term plus M J tilde sum over I Si minus M squared N J tilde N. We also have plus M J tilde sum over J Sj, okay, and we also have minus M squared J tilde N. Okay, so here we have N plus N minus M minus M. So all of those, they contribute to minus 1/2 N M squared J tilde. Okay, what we are left with? We are left with mu 0 H sum of I Si, M J tilde sum over I Si, M J tilde sum over J as J. We don't care about the dummy variables, what we are calling them. So this is simply minus mu 0 H plus M J tilde, all of this multiplied by I Si. That's it. This is our energy. Now, what is the difference? Why it's positive?
Because you have negative.
Negative. Okay. Yep. Thanks. There is a half where? Here, no, because I have two of them. I have two, this and this. Right? So there is no half over there, but there is a half over there. This term is correct. Now, if you're forgetting about this term, what it looks like the non-interacting case, right? Because we do not have any interactions. Okay? We have some sort of a field which is acting on all the different particles, and all the particles are independent of each other. Why it's called the mean field approximation or effective field approximation? Because we don't have only mu 0 H, okay? which is the natural field, the external field. We have an additional contribution, which is mj tilde, which is what? This is the point of our approximation. We approximate the effect of all the other spin as some sort of an effective field. Okay? We don't really know what this effective field is, okay, but it's there. It's an internal parameter, this m. Okay, so we're absolutely ready to solve the Ising model using the mean field approximation, okay? Because we can write down z, what is z? A sum over si equals plus minus 1, s1, s2 equals plus minus 1, etc., of e to the power minus beta, and inside here we have 1/2 m squared j tilde n minus mu 0 h plus j tilde, let's write it down over here, minus mu 0 h plus mj tilde, sum over I, si, that's it. Okay. We can take this guy out. Z equals e to the power minus beta 1/2 m squared j tilde n, multiply this summation over si of what? Of e to the power beta mu 0 h plus m j tilde, sum over I, si. This is the partition function of non-interacting particles. We solved it already. Okay? We have the exact solution. What is the solution of the non-interacting case? Okay, this is the hyperbolic cosine that we obtained in our last lecture. Okay. So z equals to e to the power this minus beta over 2 m squared n j tilde, and here we have 2 hyperbolic cosine. The only thing that is different between the non-interacting case and our case is that instead of mu 0 h, we have mu 0 h plus mj tilde, but those are constants. We don't know what m is, but this is a constant. Okay, so we plug it inside. Mu 0 h plus mj tilde. Okay, that's it, to the power n. Now, as you know, the moment we have the partition function, we're basically done. But it is not always true. Especially it's not true when we included in our solution something that we absolutely have no idea what it is. Okay, so what is this m? The solution is great if m exists. Yep. Beta, 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 yeah, you're right. Absolutely right. Yep. Thanks. So what is m? We don't know what m is. Right? We said if there is m, so this is the solution. What is m? We don't know what m is. So I've already told you, okay, we need some additional bit of information about the system. How we're getting it, or where we're getting it from. First of all, let's look on the free energy of the system. What is free energy? Minus 1 over beta log of z. Right? This is the free energy. Let's write it down. So the free energy, we call it mean field, free energy in the mean field approximation. So it is minus k Boltzmann or let's use beta, minus 1 over beta, and the log of z, okay, what is the log of z? It is, this guy contributes minus beta divided by 2 m squared n j tilde, okay, and here we have plus n, okay, a log of what? Of 2 hyperbolic cosine of whatever we have inside. Beta mu 0 h plus m j tilde. We close our parentheses like this. Okay, this is our free energy. It's not really helpful because still we don't have a slightest idea of what m is. So this is the free energy of the total system. Let's write down, because we have n here and n over here, and free energy is extensive quantity, so at least here we are right. Let's write down free energy divided by n. So what it is, this is the free energy per particle. Okay, so what we're having, beta and beta over here disappears, so we have 1/2 m squared n, no, not n, j tilde, right? Plus a log of 2 cosine, hyperbolic cosine over beta mu 0 h plus m j tilde. Divided by minus beta. You're right. Minus 1 over beta. Okay. We're still in trouble because, well, what is m? Now here comes our very nice physical intuition. The free energy, whatever m is, what is free energy, okay, at equilibrium? M is our external parameter. Let's assume that we can vary it. Okay, what is going to be the free energy in equilibrium? Minimal or maximal? Do you remember? It's going to be minimal or maximal. Minimal. Okay, it's going to be minimal. We use the second law of thermodynamics in order to prove this once a while. So let's use m as our internal parameter and say the following. M should be such that df mf by n to dm equals 0. Okay? Because the system should be at its being the correct variable. What we're assuming, there is some extensive field. Okay? It's not a field that I'm applied, it's a field that the system is applying on itself. So we're saying it's some sort of an internal parameter, and we expect the system to be in such a state that its free energy is minimal under the application of this internal parameter. Okay? This is why we're looking at the minimal situation. So I have an exact representation of f, okay, and I know that I can maybe find m, okay, or solve this equation when my free energy satisfies the second equation. Okay, so I have an exact representation now. I should take this derivative of this exact representation in order to solve what m is. Okay, so if I'm taking a derivative of this guy, okay, if I'm taking the derivative of this guy, I'm going to have m j tilde, okay, and eventually over here I will have minus hyperbolic tangents of what? Of beta mu 0 h plus m j tilde equals 0. Okay? If I take a derivative of this with respect to m, this is what I'm getting. The first time is clear, the second term is also clear because it's a cosine, and etc., etc. This is, what's the mathematical term? Oh, this is an equation that nobody can solve. Okay, exactly. And we will see next lecture how exactly we solve it find M and find if there is a phase transition or not. See you next week.